want to talk about sharing control with a human operator, but I'm not going to talk about that very much. I'm mostly going to talk about geometry. And first I want to acknowledge two grad students. Emma Treadway just graduated this last August, and Volkan was my first PhD student. So this is spanning my entire career here at Michigan and dates back to my postdoc. I'll be featuring both their work today. It's all about following a path, simple geometry, and in 2D in the plane, we know this problem quite well. Producing path-following behavior from a vehicle, here the kinematic car, could be the bicycle model, is a relatively straightforward task. If you're on the road, in particular if you're in the middle of the road, just follow the path tangent. But if you're off the road, you got to do something a little bit more sophisticated. There'll be a steering angle that you need to control. If all you do is follow the path tangent, say of the closest point to where you are, then what you'll do is reproduce the shape of the road, but you'll never get onto it. So we'd like to actually steer back onto the path, or what I'm going to say, stabilize the path. We could say you want to drive down the heading error, which I've indicated here, not labeled, and also maybe the shortest distance to the path. One very common way to do this is to use a look-ahead distance. I might find the closest point to my path by, say, just expanding a radius around some point on the vehicle, and then going a certain path length ahead or distance ahead on the road, and then direct my wheels to that look-ahead point on the road. This is very common control. I am not going to adopt it here. I'm going to try to come up with something better. This has faults. I'm not going to go into what they are. The kinematic car or bicycle model, let's simplify that. I don't even care. If we want to, we can add that later. Let's just stabilize a unicycle. I've got only the heading to deal with and a point that signifies my configuration. In fact, I'm going to remove the lane markers. All I care about is the center of the path. All right, so to define just a tiny bit to begin with, I'm going to call a point a candidate point on the path F, and the point of my vehicle G. There's a heading, and that's because it's a unicycle. It's a non-holonomic control problem. I can't control position directly. I can only control heading and then integrate as I produce motion in that heading to produce a path that G makes. The path that F makes is predetermined. All I'm going to do is find F on that path. And I'll also be talking about an error vector. Let's call it G minus F. Okay, so geometry is all I've got to talk about today. And I'm going to be referring to all these folks. Euclidean geometry, of course, Pythagorean theorem, we know and love, and all these guys. So Gauss and Weingarten are going to be the pinnacle of my talk. Serret-frenet is where I'm going to start. I am not going to get to Riemannian geometry, but you'll see how we might go there later. And all of these characters I'm sure you recognize. I'm even going to talk a little bit about the frame of Darboux, and the Christoffel symbols are going to come into play. And those guys at the top, Dennis didn't know who they were either, and I'm also going to punt. I don't know who those guys are. They still are alive up until 2020, and very hot topics. I'm not going to go there. I'm drawing a line. Darboux is as far as I'm going to go. I don't know what to say about the rest. We have path-following control applications abound. Naturally, the simple robot. There's pretty complicated paths. If you don't follow them precisely, you are in danger. Automation, autonomy in the car is a big deal, of course. But these are all, across the top row, are planar path-following problems. I'm also interested in following a surface, like, say, surveying the hull of a ship. Landing, this is, I suppose, a planar problem as well, but you're landing a plane onto a planar surface, maybe a line or a straight path on that planar surface. What if you wanted to land a plane on a curve? I don't know why you'd want to do that, but maybe. Or on a mountain top, so it could be on a surface that's got curvature. Here's following a path with a robot. I'm also going to talk just a tiny bit about human-robot interaction, which is my primary research interest. And like Dennis Bernstein said, that thing is stabilized. He highlighted the features of control. Somehow it got there. It had to have followed a path as well. Okay, division of control. When we have a human who wants to be in control, we've got to divide the labor or divide the control problem into parts, one of which we'll give to the human, the rest of which we'll give to the automation system. So I'm quite interested in that, and here's one such division. A trajectory is of course a path plus timing. The path includes maybe start and goal, and some tangent that might be described as a function of path length without no description of time. It's just space. Time, you say, I might give to the human to control. So the speed along that curve will be, and we're quite familiar with this, right? You have control over the gas pedal, and you might give away control to an automatic steering system. Well, or maybe the other way around, of course, where it evolved first, but you might imagine. Put path and speed together, you've got the trajectory, and you have done a division of control between an automation system and a human. So it's a type of control sharing. We, in the terms I've introduced so far, might describe it as having given the control of speed in the direction of TG, the tangent at the point G, to the human, while the automation finds the closest point, I'll call it F star, not labeled, or here it is labeled, on the path that's given in dotted line. And the automation also controls the heading or the direction cosine angle that the tangent on G makes with the tangent at F, or F star. This is one nice way to do it, and it'll be something I'm going to look into. Well, what if we generalize this? We saw applications. What if we generalize this into controlling a point in 3 space that generates a space curve to meet and follow a space curve? So here's my space curve generated by point F. It's got a tangent vector, but also a normal and a binormal, as does the point G, a normal, a binormal. This is a trihedron. There are mutually orthogonal and of unit length or orthonormal frame. We call them a trihedron, both at point F and point G. They orient both these frames. But all we're trying to do is drive point G to meet F and the path given. I call it CF. We might let the human control the speed. Now there are 3 angles, but one of them doesn't matter. One of them is roll about the tangent point. I'm going to leave that out. But I do need to control the orientation that the frame G makes in frame F. And I'll do that with 2 angles. I might give the control of both of those angles to an automation system and still let the human control the speed. That's a nice thing. How about controlling in 3 space again to stabilize a surface? Again, the error vector G minus F and 2 frames. We'll talk about that. Here there are 2 options. The first, I divide the labor basically the same way, and it's really no different than following a space curve. It just so happens that that space curve is embedded in the surface. Well, if I'm interested in only giving the control of one angle to the automation system and leaving the other in the hands of the user, what's that like? That is, there's a tangent plane at point F to the surface. Fu and Fv, those are the partial derivatives with respect to the path or the surface parameters U and V. I'll define these in more detail later. But there's a tangent plane, and there's a projection of any one of those vectors onto the tangent plane, in particular the tangent Tg onto the tangent plane. You could leave that in control of the user. They would be free at any point, like instantaneously, to still control the heading, one of the heading angles that the tangent projects onto the tangent plane. The tangent TG projects on the tangent plane at F. So that'll be of interest. I'll define these things in more detail later. Just to say that there are various ways to divide the control problem. And it gets more and more interesting as we let the dimensions grow. Okay, so sharing control between a human operator and an automation system is a project that takes many forms in my lab. One of them is control sharing in an automobile. You might transition control with hands-on, hands-off, kind of standard. You might also use a steer-by-wire system and couple the steering wheel to the tires with a teleoperation controller, or decouple it and give the control of the automation so you even have it decoupled. You could give force feedback if you want to the human, but that's one way to that's another way, second way to transition control. Another way we think about in my lab is the fact that we can change the impedance. If the human relaxes and there's a high impedance on the part of the automation can backdrive the human and has more control. If the human wants control, they can co-contract their muscles, grip harder, and override the automation, especially if it has a lower impedance. So we call this haptic shared control. Just another kind of control sharing. Wanted to highlight that. Different than what I'm going to talk about today. Just to emphasize, indeed, the human has a finite backdrive impedance. Here I model it simply as a spring, KH, and what we do in haptic shared control is implement the automation system with a finite gain, say very simplified model in proportional control with a virtual spring KA. And the two can fight each other. Here's kind of a physical equivalent with a spring and a set point for the automation and something in the mind of the user, theta H. Well, what they're feeling in their hands is, of course, some other angle, well, which is the steering angle, and it's coupled. Okay, so these are options. I'm not going to talk about that so much today. I just want to highlight control sharing, choosing how to do it between a human operator and automation system is an important topic. Okay, I wanted to pick up on another theme that Dennis Bernstein in his talk elaborated. Remember the Snowman. He highlighted feedback control is very powerful. We have the sensor inside the room and we use feedback. We don't even need a model of the thermal dynamics of this house. He also introduced disturbance feed forward. If you put the thermometer on the outside of the house to pick up what the outside temperature is, you can use feed forward control, incorporating a model of the thermodynamics of that house, a thermal model of that house, and you've got better control. You can have faster control. You need a good model, but you're going to have faster response. He also highlighted the idea of what he called co-located feed forward. If you put the actuator out to squash the disturbance in the first place, you're going to have very good performance. You're just going to need a lot of authority. I want to highlight a distinction now between authority and autonomy. I see a problem with this diagram so far. There's no human in the loop. Humans want to be in control. They are, in fact, averse to giving up control to an automation system. In fact, why do we call it autonomy anyway? We should call it automation, but autonomy is the wrong word. Autonomy is what the human wants to retain. They want to be in control. Okay, so this is an important feature, and I'm going to take Dennis's model one step further. This is what we should really use with a human still in interaction with his system under control of interest, the Snowman. We can provide him the autonomy. We just need to cool the house down. That's my proposal. Okay, no, not really. So the other application for control sharing that I'm going to talk about today is Cobots. These are collaborative robots. They're intended to share control with the human user. They're all based on rolling contacts, and there's no drive at any of these wheels. There's only a motor at the steering. So you set the steering angle, and they thereby specify a path or an allowed direction of motion. and then the human pushes. They won't move on their own. They're in fact inherently passive because there's no caster on any of these wheels. But what they can do is constrain the motion. The human will push, and this robot will determine what direction the human is going to move. And that's exactly the kind of control sharing I'm talking about. There's a path to be followed, and there's pushing along that path or the timing to be determined by the human operator. And there have been several different instantiations of these things and envisioned applications, assembly. None of this really took off, though. I'm going to highlight this last one in a moment, though, for rehab purposes. The Unicycle is the simplest cobot. Just want to highlight in a few terms. A human user might, now there's a frame not shown that sort of maintains a vertical axis on this unicycle, and there's motor here to move the steering angle or control phi. A human user would push in some direction F, which I've decomposed into what I'll call the tangent and the normal direction along some, well, constraint. So here what we're trying to do is impose a constraint or create a virtual wall, such that when the user pushes, they can slide along the wall but not into the wall. They'll feel the reaction force from the wall. In fact, that reaction force comes off the contact from the wheel. What we'll do is steer the wheel in whatever direction the user is pushing to create a kind of free space, and then when it contacts some virtual wall, we'll steer as fast as we can to remain tangent to the wall. And in fact, if there is an error, which there inevitably will be, we'll control or steer so as to remove that error as the human moves along. So it's all about the automation or robot controller choosing the angle phi, which sets the allowed direction of motion. And this is one of my good ideas that's never taken off. If you had a shopping cart, I highlighted this before, but just want to try to sell this idea again. If you had a shopping cart with motorized wheels and you wanted peanut butter, and you didn't know what aisle the peanut butter was on, you just plug in or say peanut butter to the silly microprocessor on board not shown, and let the shopping cart take you there. All you have to do is push and you'll feel it. You don't even need all four wheels to be motorized. You can just leave the back ones fixed and motorize the front two, and you can like push around and you'll end up at the peanut butter. Very nice. Okay. Don't know if I've inspired anybody, but in my lab, we've been interested recently under an NIH grant to apply this cobot technology to rehabilitation in a rolling wheel instantiation. It might look like this. There's a motor not shown. There's a rolling contact really not shown, and a motor to drive the steering angle right there. The human would push on the handle, and basically you can specify a motion so that a person with perhaps a motor impairment could have some assistance as about where they're going. So there's the directions of allowed motion. We thought it might be quite interesting to talk about more than one degree of freedom or a planar surface. And one direction to do that would be to make the device wearable, remove that ground contact, and then even talk about motorizing, or sorry, not motorizing, but constraining the motion of more than one joint. You could constrain, for example, two elbows, and then you're able to drive, say, an impaired elbow with a less impaired elbow and assist yourself, so it becomes self-assist. We were quite inspired also by some of the, let me play this little video real quickly. So I'm sure some of you have seen in robotics, it was quite the, milestone that here you have a fluid circuit, and there's a, you'll see in a moment, someone is teleoperating this robot with a passive hydrostatic transmission, and really it achieves a very high bandwidth and a fair amount of force support, constraint force support. Let me see if I can, well, in any case, it's teleoperated. Oh, there you see. So it's teleoperated. It's really quite impressive. So we were inspired, and they're using rolling diaphragm cylinders and hydraulics, water, not air. And we see applications for both the upper and the lower limbs. Here's some kind of things we might do in the lower limbs, assist foot drop, say. And we need a programmable transmission ratio, that's another story, or sort of assist a more impaired limb with a less impaired limb. And so my student Emma Treadway built several devices. Here's with others involved, quite a few others in other labs too, David Remy, Melody Krishnan, and then Minnesota collaborated with us as well. We had a series of devices and a few experiments that we talked about. So these are applications. I want to develop the math. We got very far, but we're still moving on the math, believe it or not. So that's what I'm going to talk about today. If you're off a path, you need to get back on. I called it stabilizing a path. Just to highlight in these fluid or hydraulic cobots, a path excursion might occur because of compliance in the circuit. Whereas in the rolling contact type cobot, an excursion might have occurred because of slip or side slip. So there's different kinds of implementations. Very interesting chart here. I'm going to get into this again. We are, and I've already mentioned sort of things in 2D and 3D. I can argue for higher D. And we need to go to Riemannian geometry. You'll see the need. In the plane or in space, I might want to constrain a curve, a planar curve, a space curve, or a surface. That is, and builds on up. Okay, planar curve, space curve. There's other kinds of space curve on a surface, and these are some of the charts I've already shown you. Let's get into the math. All right, so serret-frenet is a set of formulas. There are two of them. There's only two of them in the plane. They are the equations for the normal vector and the tangent vector and their relationship. They're derivative relationships. So if I differentiate the tangent vector with respect to the path length, which I've called SF here, I will get the normal vector, which is also of unit length, but it's scaled with kappa, the curvature. And if I differentiate that, the normal vector, also with respect to the path length, I get minus kappa, okay, in the tangent vector direction. And this is it. Here they are laid out in a sort of matrix notation. I've got a row. In the row, I've got the tangent derivative expressed in terms of the tangent and the normal. And you see we kind of got a little skew symmetric matrix here. In 3 dimensions, I have a skew symmetric matrix too, where I've introduced not only kappa, the curvature, but also lambda, the torsion. There are these two parameters, they might be parameters or functions of time, that generate a space curve. And the serret-frenet equations look like this in 3D. I could, if I specify the torsion and curvature as functions of time and integrate this equation, which is an expression for the angular velocity of a frame F in the Newtonian reference frame N, I will achieve, okay, I might integrate certain equations, and here I have space fixed, space fixed, body 3, space fixed, whatever you want to call them. These are 3 Euler angles. There are 24 sets. I'll choose one of them. I choose certain ones for certain reasons. Here's a space curve I generated with a certain here. I got a couple animations I can run. These are different space curves I'm generating. You see the frame, the trihedron, all unit vectors in this case, the tangent, normal, and binormal. And here's just another expression of the curvature and torsion, generating different space curves. Okay, these might be curves that I want to follow. They're just generated as I go. I might specify a curve with curve and torsion. So here is a simple curve. I'm going to generate the point F, and here I show it as a vector, a reference to a Newtonian reference frame. And there are my serret-frenet equations in slightly different notation. Here in 3D, I've already shown you this. I just want to show it to you in slightly different notation so that I can generalize up to 4D. And here you are. I'm sure you can visualize. Whoops, I'm sure. You see it. I'm sure you can visualize this. I used a few colors to give you the chance to go beyond the 3. But here's that skew symmetric matrix. Chi 1, chi n minus 1, these are all different curvature torsions. The space curve. This is also background still. Sorry, the surface, not space curve, the surface. I can specify a parametric surface, I'll call it S, with 2 parameters, u and v. U and v describes, or the function f of u and v describes a map from what we'll call a Cartesian space in the parameters u and v. There's a map into a 3 space, right? And you could trace out a space curve with each tracing in constant v while you vary u, or vice versa. If I want to find a frame at the point f, I might differentiate f with respect to the parameter v and the parameter u, and I'll get these 2 vectors fu, fv, and they will span the tangent space at point f. And then take the cross product of those and normalize it, I'll get a 3rd vector m. Now, most importantly, this frame, fu, fv, m, is not orthonormal. This is going to be a big deal. How do you handle non-orthonormal frames in convenient manners? We're going to pick up on that. Because it's not orthonormal, what we're going to need to keep track of are special metrics. Here I have what's called the first fundamental form, the the dot product between fu in itself, between fu and fv, and then fv in itself. These are 3 scalars. We're going to call them ef and g. There's also, and what you have with ef and g in a sort of quadratic construction between any 2 vectors x and y is a inner product. This is the inner product you need to use if you want a metric on, it's called the first fundamental form, on a surface. And there's, this is what generalizes path length using the 2 parameters u and v. And we use it to, characterize area and whatnot on the surface. The second fundamental form here, I'm not going to talk much about how it is important. We're going to need it, though. It's going to show up. This is when you take the partial derivative again of fu, call it fuu, and the dot product of that little vector with the normal to the surface normal at point f. And here's fuv and here fvv. These are, I'm going to call lowercase ef and g. These are going to show up and be quite important. In fact, what we have are expressions for fuu, fuv, and fvv in terms of the frame given, fu, fv, and m, the frame that I drew here. So there's that frame, it's non-orthonormal, but in terms of, those vectors, what we have are expressions for those 3 items, fuu, fuv, and f, and in there, all these coefficients, gamma, blah, 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 which are called the Christoffel symbols. Christoffel symbols of the second kind. Here they are, just a bunch of functions. What's interesting here is that they are all just the scalars of the first fundamental form and the derivatives, partial derivatives of those scalars with respect to u or v. Z0 is, where did I put zeros there? Oh, I forgot to put Z0. Z0 is EF minus F squared or something like that, EG minus F squared. The expression here, which we're generating, these partial derivatives, are the equivalent to serret-frenet on a surface for a non-orthogonal reference frame. But they're only half of the, well, 2/3 of the story. The other third of the story is what are the derivatives of mu and m of m with respect to u and v, and they are here, and these are called the equations of Weingarten. Okay, Gauss-Weingarten gives us the moving frame at the point F in analogy to the serret-frenet equations for what was in this case an orthonormal frame. Because it's not orthonormal, there's a lot more going on. Okay, and we're going to have to handle all that when it comes to play. Okay, That's all by way of differential geometry standard stuff. Here, I'm going to finally do something a tiny bit more modern. In fact, this is robotics, very standard robotics. If you want to find the inverse kinematics, here's a good way to do it. Not analytically, what we're going to do, instead of, for a certain robot, you can find the analytical inverse kinematics, but it's not good for any other robot. If I've got the kinematics, K, a function of the joint angles to produce the end effector position, what I might do is differentiate that expression, and I've got what you call the differential kinematics, and out pops this coefficient, J. It turns out for almost every robot, this is linear in the q dots. I can produce the task space velocities in terms of the joint space velocities, and it's a linear map. And this is like a boon. This is awesome. I can invert linear things, well, at least sometimes. So long as J is not singular, okay, and we can talk about that later. So long as J is not singular, I'll invert it and then integrate it, and I got what I wanted, which was Q in terms of X. That's the inverse kinematics. Forward was X in terms of Q. What I wanted was Q in terms of X. What does that mean? What's the inverse kinematics? That's how do I configure the joint angles to put my end effector at a desired location. Call it XD. I'm here at X when I give it Q1 and Q2. So what is Q1 and Q2 given another X? Well, okay, so I have to integrate something. It's actually no problem whatsoever. Here, you just got to parse the LaTeX, sorry. The only issue is that I might like drift. When we're integrating something, drift comes into play. Well, it's not a problem. Let's just add feedback stabilization. Here I've got the inverse kinematics again. Q dot is J inverse of Q. So I got Q dot is J inverse of Q times, and I'm going to now do, I used to have X dot, but I'm going to integrate that. Okay, so here I integrate Q dot to get Q. Q dot is an expression which I'm going to now design with a feedback law. U is up for me to design, and I'm going to design it here as K times an error between XD and X, where X is available if I've got Q. That's the forward kinematics. Those are easy to run. So we call this the feedback stabilized inverse differential kinematics. Kind of a long name. But just take this control law, which is represented here in the block diagram. I've also got XD dot there. And plug it in. The error derivative, the derivative of the error, XD minus X dot, if I plug in with this control law, sorry I didn't substitute the equations, produces E dot equals minus KE, which is beautiful. Stable, exponentially stable. Works like a charm. The idea that I'm going to use for stabilizing to a path is going to be just that. I'm going to integrate the inverse kinematics. Let's just make up the kinematics. Kinematics is going to be involving the error vector, G minus F. All right, so I've shown, here's F. Okay, that generates the curve I'm trying to follow with path length SF. G is the robot that I'm trying to stabilize back to the path F. Here, the heading is not very good. If I can express G minus F, and what we're going to do is express G minus F in a particular frame. We're going to choose the frame here, this serret-frenet frame that we've been talking about so far at point F. There'll be two measure numbers. I'm going to call them alpha t and alpha n for, subscript in the t direction, tangent direction, and subscript n in the normal direction. I've got two measure numbers of the error vector. If I were to drive both of those measure numbers to 0, I would be on the path. Further, there's a division of labor here, a division of control. If I drive alpha t to 0, then I have F at the closest point. Because then alpha n is the closest distance. G would lie at NF. if alpha t were driven to 0. You see how that's going to work. I have a error, a heading error that I could define theta, which is the angular difference between these two frames I've defined. So our plan is to control SF, the path length along the curve generated by F, to drive alpha t to 0. That'll give me the closest point. And then I'll steer theta to drive alpha n to 0. That'll converge me to the path. The whole while, the human can do whatever they want to control the speed of how this thing happens. Okay, so that's the plan. The error vector, so that would be my differential kinematics. Sorry, actually, this is not even differential. We haven't differentiated anything yet. This is analogous to my forward kinematics for the robot. I'm just going to take a vector alpha t, alpha n, put it together into a little column vector, take these two headings, TF and NF, or the parts of my serret-frenet frame, and line them up so I got a nice little matrix expression. Psi alpha expresses the error vector. Where here I can invert that, express the measure numbers in terms of the error vector using psi transpose, because psi was an orthonormal frame, its transpose will be its inverse. That's key, but we're going to lose that later, as you know, when we go to the surface, because we're not going to be having an orthonormal frame anymore, so we're going to have to invent something, but we'll get there. Okay, we're going to differentiate this to get the differential error kinematics, and we're not doing this to get something linear. It actually already is linear. We're doing it for other reasons, basically to split the labor, make things in terms of speed. But here we are. Differential error kinematics are pretty straightforward. I can differentiate all these guys. Let me move forward a little bit. Differentiate all these guys. In the process, I'm going to invoke serret-frenet. I'm going to substitute for psi dot. Psi, as you know, was TFNF, and psi dot is going to be, well, there's serret-frenet. Just plug right in. And we can, in this matrix expressions, multiply these things together, and then we have that little matrix of scalars that's skew symmetric. And a couple other things involving elements of the direction cosine matrix between these two frames. And something else lying around. I can put this all together. In fact, I can define this a nice little matrix expression. I'll call it M, a function of alpha, the measure numbers. And U is going to be something, okay, these are the two things, that's my control. I define my control law, U, SF dot, SG dot. SF dot I'm going to give to the automation, SG dot I keep with the, I give to the human. Let's just suppose at the moment I give them both to the automation for purposes of lining things up. If my differential kinematics are right here. I'm going to express the control as M inverse alpha nu. That's so simple, and nu is just going to be minus k times alpha, so that when I substitute all these in, I get A alpha dot equals minus k alpha, or exponential stability again. And here we are in the kind of block diagram. This is super simple. I might remind you of feedback linearization. That's what this is, in effect. In a simplified sense. And there's a trick I can do. I don't really need to integrate alpha dot if I don't want to. I can express alpha if I've got the forward kinematics. Just by the way, not a big deal, but it's a nice debugging tool. If there's a B term, okay, B, I haven't defined yet, but let's just suppose that there's something else involved. At the moment, my differential kinematics that I showed you was so simple, alpha dot equals mu. Well, what if there's something else? Could I handle it? I can with feedback linearization. Define U, the control law, in these terms, and when substituted in, we still get minus k alpha. There's a little cancellation goes on there. That's standard feedback linearization, and there's still the switch that I can throw for checking purposes. I don't actually need to integrate alpha dot. Or, instead of grouping everything together, I can partition it. So this is a 2x2 matrix M in stabilizing the planar curve. I can partition M into a first row and a second row, and basically there's another sort of block diagram that I can draw with these two things partitioned out, and I'm doing this to prepare for giving one of these to the human instead of retaining them both for the controller. And I don't need to go through the math per se, it's just very straightforward. I've got a matrix expression that it can easily partition into two scalar expressions, and there's coupling between the two, and it doesn't involve B, and that's why I did it. I needed this B because basically it couples the two. It's kind of cool. All right, so here's a very simple Mickey Mouse, but it was sort of easy. Yes, I'm stabilizing. In fact, this is not, I mean, I can demonstrate everything I think should be working because it's not all working yet, but, and I'm doing it myself. So, yeah, I've got a path G and a path F. F is a circle, G is a line. I can choose different headings. I can change the circle size. Everything works very beautifully. It stabilizes. This is not path following. This is just finding the two positions, finding the two path lengths, SG dot and S dot and SF dot, and integrating them until I get the two to approach. So this works as expected. If I want to steer instead, I can set this up, but I'm not going to do it with feedback linearization. I'm going to use a control Lyapunov function. So here, define my control Lyapunov function in terms of my error vector measure numbers and a heading error, which I'm going to define as theta minus delta, where delta is an approach function. This describes how am I going to steer, how am I going to reduce that error vector in the normal direction, alpha n, as a function of path length. So this approach function, I'll introduce a little bit more, but delta, it's a relatively simple idea. If I take the differential kinematics that we've already developed and simply plug them in for when I take the Lyapunov function derivative, I got alpha alpha dot. If I plug in this for alpha dot, here is what I land with, and it turns out, look here, we've got a quadratic expression involving a skew symmetric matrix, which vanishes. Kind of cool. I saw a bunch of things canceling out forever, and then finally put it in matrix forms, and now I know that they're always going to cancel out. And a bunch of things here that I can easily write control laws in the spirit of control Lyapunov functions to achieve, in the end, a negative definite Lyapunov function, v dot. I group things, I add and subtract something in order to rearrange, put something inside there that I didn't want there, and leave something else on the outside. Okay, I end up with something on the outside. I got a negative squared term, another negative squared term, very happy. And then something involving this delta function, okay, sine of that delta function, plus something else times the an, alpha n, SF dot. No problem. There's going to be a special design to this alpha function. It's going to be a negative hyperbolic tangent of something. Why? Because I found a paper, and it worked, and I was so pleased. I'll tell a little bit more about that paper in a moment. But here's hyperbolic tangent in blue. Here's the sign of that hyperbolic tangent in red, no big deal. And then if I've got a alpha n, which is positive above 0 and negative below 0, like it naturally will be, and if SG dot is always positive, or I'm moving forward, which I can pretty much guarantee. Okay, we'll do something. If I'm moving backward, we can throw a switch. But okay, so I'm moving forward, and okay, yes, something is positive above 0 and negative below 0, and put it in as the argument. You get something, as the product of something that looks like this, and also we're happy. We get yellow. It's negative definite. It's beautiful. by design, and I found it and borrowed it, and that's what we did. I actually already introduced most of this. Let me just show you a few simulation animations. This is steering to approach a circle, simple planar curve. Okay, steering to support something more interesting than a circle. You know, we do some crazy things that because we are steering in coordination with the closest point that has a frame on it. But yeah, we're getting there. It's actually kind of elegant. And yes, this is the paper by Lapierre. It's a 2001 paper. Oops. Sorry, push wrong. Oops. 2001 paper. It was following, it was a cart, sort of path following for a kinematic car. And they demonstrated. I had been doing myself as a postdoc work. This is with my student Volkan. We were doing closest point. And this was published in 2005, after these guys, although we were not aware of them at the time. I just discovered these guys in May this year. And this was me as a postdoc, 2001, doing my own version of this path following thing. But looky here, I've got a second derivative, whereas Lapierre did it in only one derivative, and it's so much more elegant. Okay, everything turned out linear and elegant for me in a second derivative, so I could partition thing. And we're not going to do it partitioned, we're going to do it with the Lyapunov function now. So that's my approach as adopted. Okay, let's do this. Let's go a little bit beyond Lapierre. Let's do this for a space curve. I can adopt a certain set of Euler angles just to be able to integrate. I'm not going to dwell on that. Everything is analogous in the space curve case. I've still got an error vector with now 3 measure numbers. I define psi is just a little bit bigger. I've got differential kinematics, which are just the derivative thereof. I still have an orthonormal frame in 3 dimensions, the serret-frenet frame with that extra parameter torsion. It shows up when substituted here and will, as you'll see, in the Lyapunov function and Lyapunov function derivative produce a skew-symmetric matrix in quadratic form. I'm going to have 2 approach functions now because there's 2 angles to handle. Actually, there's a 3rd angle to handle that I'm just going to slave to the others. Here is that skew-symmetric matrix in the middle in a quadratic expression, so that all disappears, and I've got 3 terms left. This one's quite straightforward to design with all my delta functions in it. And I got 2 things to cancel, but I got 3 angles. One of them is going to be slaved. Essentially, I have 2 angles and the path length. And I substitute that all in, and I get something that I can easily recognize given my, well, these control Lyapunov functions. These control laws will produce a negative definite form. And here's a picture of stabilizing a space curve. The curve is a kind of spiral. This is where I start. And I approach it, and I'll show you a little animation on the next slide that produces a similar following thing. So totally exciting, I think. Well, actually, just a pretty straightforward extension. The math did it for us. The surface. This I'm still working on. This is a work in progress, I'm afraid. But I want to show you what I've got and a certain breakthrough that I think I've come to, which involves the dual basis. U and V are superscripts here on purpose. The ones that I've introduced so far, U and V, are subscripts. That's the partial with respect to U and V of F. And these are whatever I need to be orthogonal to that, so that G transpose U is the identity matrix. That's called a dual basis. I can always find a basis that's dual to a non-orthogonal basis if I want to, and it's used a lot in physics, and this is like the introduction to Riemannian geometry, as a matter of fact, as I understand it. And here we are. G is that dual basis, and with it, everything turns out beautiful. And I won't go too far, but there are these Christoffel symbols, and look how nicely they are sort of arranged. There's two sets of coefficients, one u dot, the other v dot. One set of Christoffel symbols up here in the upper left triangle, upper left diagonal element, and another set here with some duplication, half the duplicated. And then P1, P2, and Q1, Q2, that came from Weingarten. EF and FG, that's the second fundamental form. They're all arranged here. These are the direction cosine of values in the first column of the matrix, and here's these two things that look analogous to what showed up before. This is looking beautiful, and if I want to, I can write this all together in a grouped form with u dot, v dot, and s dot, which are my three control variables, to be defined as u. And look again, I've got a system which looks, in these symbols, the same as my last system. It's just that m is a bit bigger. And I'm going to propose to, and my code isn't all working, but I'll show you a few things. I'm going to sweep a few things under the rug, and this is a work in progress, and yes, indeed. Okay, so I can find the closest point on a sphere, it's actually an ellipsoid, to a fixed point. Or I can let the point that looks like it was fixed is no longer fixed, and it finds the other. It happens to be on a line, a pre-specified curve G. And yeah, the next simulation isn't working. So stay tuned. I think I'm close. Emma and I are working on it a little bit together. Just want to say a few more things, and I'm going to wrap up. The frame which I've been using, FU, FV, and M, which, okay, in these notations, XU, XV, and N, whatever. There's another frame called the frame of Darboux, which is orthonormal. We have used the frame of Darboux as well, and I'm not so sure that the frame of Darboux is going to be as elegant, as a matter of fact, as the other one. There are so many choices to be made. Just to say that the geodesic curvature and normal curvature and relative torsion come out, and we have still a skew-symmetric matrix, so things might be a little bit more elegant. We lost the skew-symmetric matrix, as you know, with the frame FU, FV, N. But the frame of Darboux will be skew. Haven't decided which way I'm going to go, frame of Darboux or the trihedron. Here's a few more simulations. These are working for the most part, but not all predictably. And so I'm not going to highlight them in too much detail. Just to say that when we put these together with other things that we've got developed called the curvature transformations, which have been around for a while, we can transform from task space to joint space, and if it's a cobot, we call it piston space or volume space. These are just standard Jacobians that here at this velocity level where I've been doing everything are available. We have expressions to relate one space to the other, and they can get pretty hairy, but they are actually working in some sense. So here is some demonstrations Emma put together. These are fluid cobots. This not wearable form, but you'll see what Emma is doing here is tracing a circle. And in this case, we are not doing it with the methods that I've introduced today. Instead, we're doing it with simple switching of constraints, which are always just lines. So what I'm talking about today are all continuous curves. Just wanted to highlight some of these. This is a complementary work to what I've been talking about so far. It just has all piled on task space, joint space, and here we're stabilizing to a line, and there's feedback control involved here, and that's it for today.